all of them, LPG, Carbon 5, Collab, Emma, Society of Work, EPB, and of course, UTC. So their money equals the food that's getting into your belly, and that's a wonderful thing. So I think that's pretty much it. Anybody want to, any other events going on that we need to give a shout out to? No? Okay. Come out Saturday. It's going to be a good time. I'll be there, and a lot of other CHADEV friends will be there as well. So, yeah, Sam here. Sam Lensgraf, is that right? Yeah. Okay. Sam approached me a number of weeks ago and said, hey, I've got this paper that I've co-authored, and I'd like to talk about it. So it's not very often that we get presentations on award-winning papers. Sam tried to tell me the name of the conference that this was awarded at, and I quickly forgot it, but I'm sure he'll tell you. So Sam is a software engineer at Bellhops, and we want to give him a warm welcome, so everybody give it up for Sam.
All right, thanks, guys. So again, I'm Sam Lensgraf, and I am kind of a back-end software engineer at Bellhops. And I'm going to tell you guys today about kind of my journey in learning about how 3D printing software works and the specific angle that I'm working on to make 3D printing faster by just improving the software that actually drives the 3D printers. So I'm going to try and keep this talk kind of high level and really visual, so it's not overwhelming you guys with just a bunch of math. So kind of an outline, I'm going to give you a brief overview of what 3D printing is. And then I'm going to explore the idea of what is a robot motion path or a tool path. And then I'm going to talk to you guys about kind of the standard way that tool paths are represented, at least the way I understand it. And then I'm going to kind of go through my research and how it actually applies to the space. So here's kind of a time lapse of a 3D printer doing a 3D print. It's important to recognize that the 3D printer is kind of building this model out of smaller steps that it's actually putting together to make something that's beautiful, which I think is a really interesting process. So basically, this 3D printer is drawing its substrate up through its nozzle and is forcing that through a hot end, which then deposits it out in layers like that. So it's the job of a 3D printer to decide how can I move in such a way that while I'm squirting out plastic, I'm going to actually build a part. So my work, I abstract the 3D printer a lot. I actually abstract it to a rectangular extruder, which bears the rectangular hot end, or print head as we call it. So this print head often hangs a little bit below the extruder, but it doesn't have to for my work to apply. But just keep in your mind that this hot end is what is actually flying around and doing the printing in our context. So 3D printing software is basically a compiler for geometries. So the 3D printing software's goal is to take this mesh and then to represent it as a toolpath. So on the right side, you see kind of my software's representation of what a toolpath is. And the gray parts are what is printed, and the red parts are actually motions that are wasted during the printed process. So if you're going to understand what 3D printing is, it's really important to understand what a mesh actually is. So for 3D printing, we often represent a mesh as just triangle soup, or a list of triangles in 3D space. But there are a lot of different ways to encode meshes, and every different CAD software is going to do it a different way. A really popular way of representing meshes to hand them off to different people is called STL files. And so an STL file is just a list of triangles. And as far as I understand, it's primarily used because it's really easy to generate an STL file and to parse them into your own representation. But you often have to structure them in a certain way, and I'll talk about that in a second. And then also you have to understand what a toolpath actually is in the context of a 3D printer. So a toolpath, whenever you're talking about a robot or a 3D printer, is just a very precise description of what actually has to happen in all of the different elements of the machine that are computationally controlled. So you can see the firmware detects these kind of G1 movements, and that says, okay, move here. And then so G1 takes a 3D point and an amount that it's going to extrude for that 3D point, and it constructs the part out of these very simple elements. These can be encoded in a lot of different ways, but I use G-code personally. So I just want to kind of drive home the generality of the idea of a toolpath. So you can think about a toolpath with this guy who's carving out stuff with a chainsaw, which is my favorite example. So it's sort of a simple thing for a human to just kind of move around in 3 space and carve out some interesting thing from a piece of wood. Well, it's not simple, but you can do it if you practice. But the complexity of what he's doing is huge. And there are a lot of these kind of logical guarantees that are just built into the way that we move that we have to build in again into the way a 3D printer or any robot is going to move. So in an illustration of some of these invariants, the guy basically does not want to cut his arm off, and he doesn't ever want the chainsaw to touch him while he's moving it around the block of wood. He doesn't want it to touch his dog, and he really wants it to be touching the wood and actually, he wants to generate his sculpture. That is his goal, and he wants it to stand up. So to bring this concept back to the idea of 3D printing, if we're going to have kind of a general way of creating toolpaths for 3D printers, we have to define the logical invariants that we need our toolpath to be able to guarantee us. And so for my work, what I use is that the printer will not run into itself, and the printer will not run into something that it's actually already printed out. So if you can visualize, if you run into something that you've already printed out, you melt part of your model, or you knock it over, or you just generally cause yourself problems. And then finally, every part of the model needs to be sitting on another part of the model that's already printed. So if you don't do that, you just end up squirting stuff in the middle of nowhere, and you make something that sucks. So how is it that we actually get to the point where we can do this stuff? We need to define the smallest unit that our 3D printer is able to actually handle. And so for the 3D printers that you see in kind of the wild a lot of the time, it's often basically your G-code file is a list of line segments or single 3D points, and your printer just interpolates these 3D points. So we need software that's able to work in context of these, basically they're primitives. And so the standard method actually constructs a series of layers and then does a path planning over those layers. So kind of a high-level overview of the process for an FDM machine. You take an STL file, which is the representation of the outside of the object that you want to be printing out, and then you slice it into a bunch of layers, and then you aggregate these slices into structures called islands, and then you create an infill structure over these islands. And then finally, you construct a 3D toolpath over all of these things that are in 2D. So that's where it actually becomes a 3D part. So mesh slicing is often like a really slow process. Not really slow, but it's sort of hard to get it to go very fast. So basically what you have to do is you decide how many layers are going to be composing your part, and then you take each 2D plane and you intersect it with one of these triangles, which yields either a point or a line segment or nothing at all. So what you can do is you can just discard all of the points, and then you're left with a series of line segments in each layer. And so each of these line segments are actually what's describing the outside walls of your part. So these are kind of like the meat of it. But there's actually not enough structure in these line segments for us to be able to do very interesting things with them. So we need to process them again. So in order to get these, a lot of different software will do things in different ways to speed up the process. I know Cura Engine stores things in a way that basically each triangle knows the triangles that it's touching in the mesh. And then so it can kind of walk around in this mesh and it can figure out what's intersecting. For my personal software, I use an axis-aligned bounding box tree, which actually allows you in logarithmic time to decide which triangles actually intersect with each plane. So that really limits the amount of work that you're doing on every layer. So here's a visualization for my debugging software that I wrote of kind of the result of a slicing process before you've aggregated anything. So you can see on the left all these different triangles. It's even hard to see each individual triangle because they're so small. And then on the right is the result of slicing at kind of a uniform layer height. You can't see all the segments there because they're too small and too close together, but every segment is assigned a random color in this output. So we need to kind of define a process that's going to allow us to turn these line segments into actually useful parts of the model. So down here you see kind of a visualization of 4 different islands in the model. And these islands are kind of the smallest part of the model that actually represents something that's been sliced, that are really useful. So an island is a sorting of these different contours that tells you this contour is on the outside, and then this contour defines a wall on the inside of the part. So we need these islands, and then here's a visualization of the islands having been constructed. So kind of a basic algorithm to construct these islands, which is what I use in my software, is that you walk upwards with a plane, and you yield all of these these 2D line segment intersections. And then what you can actually do is you can pick out a line segment, and you can walk around that line segment, and you can actually get around the model, and you actually get islands out. It's a really simple algorithm, but it works really well as long as it's able to handle kind of interesting things inside of the mesh. So after that, we need to make the islands actually filled with something so that you don't just have these tiny, flimsy parts. So what we do is we actually take a tessellated pattern and we repeat it over the space of this island. And then you can take the island and you can intersect it with all the segments, constructing this tessellated pattern, and that actually gives you what we call an infill pattern. So there are a lot of things to consider in this infill stage. And the primary one that I've identified is kind of negotiating the trade-off between strength and the actual print time and material cost to produce something. So here's an example of the same mesh after having been infilled with a hex structure. So you can see on the left there's a bunch of voids in the model. And on the right side, you have these really cool-looking hex infill structure. So in this, each island has been assigned a random vibrant color. And yeah. So then the last step, and the step where my research occurs, is that you have to connect all of these islands into some kind of like a 3D path that you can actually interpolate with your 3D printer. So a really simple algorithm, and I know that one of the open source software uses is basically you take each layer and you plan over that layer individually. So this gives you a lot of important guarantees about the way you're actually going to be printing out. If you're moving in 2 dimensions, you have built in all of the invariants that I discussed earlier. Basically, you're never going to run into something that you've already printed, and you're never going to run something into the printer as long as you're within the box that the printer actually needs you to be in. So the process is basically, for each layer, you pull some starting island and you append that to your path, and then you actually just connect the islands in the order of closeness. And that actually results in a really wasteful toolpath. So here's a visualization in my simulator of the same mesh being printed out. You can see that, if we go back, it's planning over an entire layer where it could be moving up before moving to the side, is kind of the point that I want you guys to see there. So you can see that it's kind of like it'll visit one island, and then it'll do everything inside of that island, and then go on to the next. And that's a pretty efficient way to do things, and it's pretty fast, but it's not the most efficient. And then finally, you have to actually take this kind of abstract path that you've generated, and you have to generate a set of machine instructions that describe this path in a way that the 3D printer can actually print it out. And so that's kind of a complex piece of software in a lot of different applications, especially if you want it to be general. And that's also not something that I've dealt with quite as much. But kind of the main challenge is how do you work with multiple different instruction sets and multiple different printer hardwares that all have their own kind of specific requirements. So this set of algorithms is really useful, but it also has some pretty important limitations. And the main one that we're actually trying to combat in our work is that it produces a lot of really unnecessary wasted motion. So if you look at this, this model kind of has a bunch of these interesting complex features, but the printer moves between each one of them at every layer. So that results in a huge amount of just unnecessary motion where the printer is moving between printouts. So our goal is to kind of try and reduce that amount. So what we did was we allowed the printer to move in all three of its axes while it's actually printing something out. And we also defined a structure that allows us to guarantee what we need to about this toolpath while actually producing more efficient toolpaths in the end. So basically, this means that we don't only print in the layers. And we allow the printer to identify these local features. And basically, it can move between these local features, and it will construct very efficient toolpaths, given a good traversal algorithm. But we also provide a way for you to limit the extent to which each one of these features is produced, so that you actually don't, so that it's easy to get an abstraction that's like worthwhile for your printer. So with these ideas, you can see our algorithm will produce the things on the right side. And on the left side, you see it without our approach. So on the right side, you can see that the path is basically able to find these little features, and it's able to move up those features before moving to the side. So with certain geometries, or if you had a lot of different things on a single plate, you're actually going to save a huge amount of motion while you're printing out a part. That's going to be really geometry dependent, but it's important if you ever want to get something that is ever approaching a truly optimal toolpath. So we had to come up with an efficient way to actually limit the amount that you're moving in these dimensions in order to preserve our guarantees. So basically, with more freedom, we have more chances to mess stuff up, and you have to have a more robust scheme for actually representing how things are moving in your model. So what we do is we generate a dependency structure over all of the different elements of this model, and we use that dependency structure to limit the way that we're moving in 3 dimensions. So this dependency structure can get really huge for big models, so it actually took a ton of like hacking and optimizing to get it to work really fast in all cases, but I think I got it. So just to reiterate, the printer does not intersect other parts of the model that have already been printed, and the printer cannot intersect itself, and all of the parts of the model must actually be sitting on something while it's actually printing them out. The way that we do this is that we take the result of creating this infill structure, and then we blow it to bits into contours. So the contours are these continuous printed sweeps that the printer makes. And we construct a dependency graph over all of these contours. And so this dependency graph is fairly easy to implement, and I'm going to walk you guys through how we actually come up with that, or came up with the ideas. So our thought is that if you can limit your abstraction of your printer to a very small portion, then you can actually get something that's useful and actually that runs pretty fast in software. So what we do is we take a small part of the extruder or the print head that's abstractable, and we abstract it with just a 3D axis aligned bounding box. So that gives us a really simple way to think about how things are moving. And I couldn't draw a 3D box in PowerPoint, so I drew a one with ASCII art. So we take this print head, and we just take everything else out, and we have this little 3D square rectangle thing that's moving around in 3D space, and that's what we're thinking about for our optimization process. So with this abstracted print head, we take all of the contours, and we construct this dependency structure in such a way that anytime a single contour, whenever you print that, if that being printed blocks another contour from being printed, all of the contours that it blocks are dependent on this contour. So with this structure that's actually really simple to say and think about, you get all of the guarantees that we needed. So we tested this algorithm on a benchmark of 403 models. And basically what we did was we took an open source piece of software and we had it generate all of the line segments necessary to print out a model, and we applied our path planning to it and compared it to their path planning. And we got a 62% reduction over the paths generated by that piece of software. 62% reduction in the amount of time that the printer spends moving between print and motion. So this translates directly into reducing print time, reducing energy consumed, and it's just really fun to work on. So in the future, I want to kind of adapt this to where it's actually like a platform that people can use to print things out, and it's actually a slicer that's useful for people. And so using that, I want to establish kind of the effects on part quality of moving up before moving out, and I want to be able to establish, you know, a physical measure of the actual print time reduction, even though it's going to be dependent on hardware. So kind of some takeaways from this. Science is really not that hard to get into, especially if you're doing something that's like really, really new and exciting, like this is. Like I think I'm one of the only researchers thinking about this in this way right now, which is why I was able to kind of get published whenever well, I also have a really good mentor who works with me. But so each of the phases with the pipeline that I introduced to you guys goes really deep. There's like 10 or 20 different papers published about all of these that I know of. And you know, there's a ton of unanswered questions here. So basically, whenever you get this dependency graph and you try and traverse it, that's actually a very, very hard combinatorial optimization problem, which is not very well researched. So if you're ever interested in like working on this stuff with me, or you're interested in like getting into 3D printing or path planning or any of these algorithms, I'd be really happy to hear from you, and you can email me at that email address right there. And yeah, thank you guys so much for coming out. I really appreciate it. It was fun.
Yeah, we have plenty of time for questions.
Yeah.
So how do you is this on? Yeah, okay. How do you handle you know, support? So if something's overhanging and you need to put support there. That
comes within, well, we actually don't do support generation. We assume that the mesh is fully supported. So given a supported mesh, we will produce an output path that is actually feasible.
Generally, the STL doesn't include the support.
Yeah, but that can be defined in a part previous to what we actually do.
Okay.
So not seeing a diagrammatical representation of the dependency graph that you were describing, but kind of thinking I understand how it might look.
Yeah.
You said it's not really well researched how to traverse the dependency graph optimally, but would that be included in like the set of traveling salesman problems? Maybe apply some of that. Okay.
So it would be asymmetric traveling salesperson with precedence constraints would be the problem.
It occurs to me that having an upside down cone shaped hot end, like a point, would reduce your dependency graph greatly. Are you interested in maybe having a custom built pointed nozzle that reduces the amount of space it takes up?
That would be awesome. I mean, that would be perfect for this kind of a thing. Yeah.
Is that one of the next steps? Because it seems that most of the commercial hot ends have been built around the idea that it's always going to be in 2D.
Yeah.
And so no one is really, that I've seen, building these long pointed tips to get the material deep down into these now available chasms that you've designed.
Yeah.
Are you working with anyone to push this? What I mean is, what's the next step?
On that, no, I'm not a mechanical engineer, so I don't actually know how to think about the temperature stuff involved with that, but I would love to work with someone if anyone was interested.
So you say you're working, when you create the dependency graph, you're working with contours?
Yeah.
So is still the first step to slice everything, and then once you have the islands, to generate the contours from the islands, or are you actually creating contours from the shape itself?
You slice everything and you generate the islands. So the islands are kind of needed to get an intelligent infill structure. So to get an infill structure, you need to know what is the outside of this part and does it have any chasms inside of it. So you basically, you take it and you do an intersection with this tessellating pattern, and then you subtract out a chasm, and that basically gives you an infill structure. And then you kind of blow those apart again.
One more question. So on FTM machines, there's a constraint that the material needs to cool down. So you'll actually see them, like the machine itself will slow down as it gets to a smaller part.
Yeah.
Have you considered that as a third invariant? Because it would actually, conceivably, it could be faster to move in space to a different part while one's cooling down than to go back through it if it's small.
That's true. That's a good thing to consider. That's not something we handle right now.
So does this work with other types of 3D printing?
It will work with any type of 3D printing that's not like SLA. So anything that's like building something up, not something that's pulling something out of kind of like a vat of something like that. I know that there has been some like really basic research on how do you use these photopolymers and actually pierce down with a laser into the photopolymer to cure it. But you know, our work would really strongly apply to that. Now, we could actually just limit everything in our dependency graph to a 2D, to basically to where you're required to do it within layers, and then all of our traversal algorithms apply again. So it would be useful for that kind of a 3D printer then.
Yeah, I've got a question. So can you talk about how you got into this?
Yeah.
This is not like something you do professionally.
No.
So.
I was in undergrad like 3 years ago, and I asked one of my teachers if I could do an independent study with him, and he said, yeah, I have this idea for a project in 3D printing. And he said, you know, I want the 3D printer to be able to go up. I think it's dumb that it goes in the layers. How can we do that? And we came up with that, and I've been working on it for about 3 years now in my spare time. And we've published a paper, and we've got another one in peer review right now. So it's pretty exciting stuff. And his name is Ram Metu, and he's very helpful, very kind guy.
So did you, like how much time did it take to ramp up on all of the required math and sort of prerequisite knowledge to do this stuff?
I delegate a lot of the math to existing libraries, actually.
To?
To existing libraries, software libraries. I use Seagal a lot. I use Boost Geometry. So the only parts that are like really mathematically intense, except kind of like the theoretical parts of doing a traversal, are the the aggregation of the layers into the infilled structures. So that I actually use Clipper for, which is a library that does curve offsetting, and it does basically intersection of geometries and contours and stuff. And honestly, the answer is I'm still ramping up on the required math. It's sort of a lifetime project to ramp up in some of this stuff.
So when I was looking at the the islands and the smallest structures that you're working with there, it looks like everything's essentially a linear function, and then you get a collection of linear functions to create your islands. Does that sound right? It's not. I guess I don't know what you mean. Like a linear function is like you're going from point A to point B in a straight line. There's not. You're not necessarily creating a 3D curve, for example, when you're as your smallest component.
Yeah, exactly. So the smallest component that you can handle is these line segments, which are they're not represented as linear functions, but they are basically that. So it's like the idea of this whole process is that you're composing these really interesting, complicated parts out of these tiny little two-dimensional straight lines, basically.
Do you think a higher order function would help you, not have to have as much wasted movement?
Yeah, definitely.
Okay, so is that something you're working towards, or is that still dependent on backfilling on the math part, or where?
I understand those mathematics. The issue is that this software takes in like a mesh that's composed of triangles. So then you don't have any information about like the curvature or how it looks other than these triangles. But there are algorithms that I know of that directly slice a CAD representation, and the CAD representations are generally with higher order functions, at least to my knowledge. There'll be like an implicit surface or kind of like a spline of a bunch of high order functions.
Any others? No? Okay. Everybody give it up for Sam. Get it, Sam. Okay, so yeah, come out next week to. I'm checking, actually. I don't remember what next week's talk is. Come on, internet. Yeah, so next week we're having Ethan Rogers come out and talk to us about a Jenkins setup. So that'll be fun. Otherwise, we'll see you guys Saturday.